far we have discussed about supersonic and subsonic flows and also sonic flows as a special case. Based on all this background that we have gathered, we will analyze a very important engineering situation, that is compressible flow through nozzles. Okay. So, to understand compressible flows through nozzles, we will first see that what is the purpose of a nozzle. So, normally this is the shape that we consider for a nozzle if we are not seriously bothering about the compressibility effect. What we are expecting, that as the fluid enters this nozzle along the direction that I am showing, its area will decrease and the velocity will increase, that is, it will be accelerated. This paradigm is based on our intuitive mindset that area into velocity is a constant or area into average velocity is a constant. This is true when the density parameter does not come as an important factor. For a compressible flow, the density comes as a very important parameter, and that makes this entire situation not so trivial. So, because this kind of a nozzle is our intuitive design of the nozzle, we will start with this, and this is called as a converging nozzle. So, let us say that there is a reservoir where there is a gas with pressure P0, temperature T0, these are all stagnation properties. And then there is a chamber which is called as a plenum chamber. What is done is that there is a way by which experimentally you can control the pressure in the plenum chamber, which you call as a back pressure. So, the pressure in the plenum chamber is called as PB, which is called as the back pressure. How do you control the back pressure? So, typically there is a valve. By regulating this valve, you can modulate the back pressure. So, somebody does this experiment that the person is trying to monitor the mass flow rate by varying the back pressure, keeping the reservoir pressure fixed. So, what is your intuitive idea? The intuitive idea is that you have a pressure. Now, if you reduce this pressure, the pressure difference will be more and mass flow rate will increase, and in this way possibly the intuition is that perpetually this mass flow rate can be increased. We will see that this perpetual nature of increase of mass flow rate will stop when a critical mass flow rate is attained, and we will understand this in a moment why. So, if you now say reduce the back pressure, the mass flow rate will increase. So, let me draw it with a different color. but when a critical pressure is attained, so which we call as P star, after that no matter how much you reduce the back pressure, the mass flow rate will remain the same. And at that condition the nozzle is said to be choked. Now we have to understand that what is this condition and what is the physics behind this choking, so that with a subsequent lowering of the pressure the mass flow rate does not increase anymore. So if you recall that we earlier derived a relationship between the change in area and Mach number for flow through variable area ducts. So when we were doing that, the conclusion that we arrived at is that if there is a sonic condition, the sonic condition, if it at all occurs, it will occur at the minimum area location, but it is not always necessary that the minimum area location will have the sonic condition. So this we must understand very carefully, that if at all there is a sonic condition, the sonic condition will occur at the minimum area. In this case the minimum area is this one, but it is not always necessary that at the minimum area the condition will be sonic, the condition may also be different from sonic. So what we want to do here is to check that under what condition, if you decrease the pressure, the mass flow rate will not increase anymore. Actually this is nothing but the sonic condition. Question is why? Why beyond the sonic condition? See, from here you are accelerating the flow in this direction, accelerating, 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 accelerating till sonic condition is attained. Beyond this you are not able to increase the mass flow rate. Why? So what happens when you reduce this back pressure? There is a messenger from the plenum chamber to the reservoir, it tells the reservoir, it gives the reservoir a message, hello reservoir, see I am reducing the back pressure, now it is your responsibility to understand that there is a larger pressure difference and please respond to this with an increase in mass flow rate. So the messenger is going from here to here with a message that the back pressure is reduced, now Mr. Reservoir please give us more mass flow. So velocity of the disturbance that propagates with respect to the fluid is velocity of disturbance minus velocity of fluid. At the sonic condition, what is the velocity of the fluid? It is c. What is the velocity of disturbance relative to fluid? That is also having a magnitude of c. What is its direction? The disturbance is propagating from the plenum chamber to the reservoir. That is how it is propagating the message to the reservoir. So this is minus c, c in this direction. That means velocity of the disturbance is 0. So the disturbance simply cannot move. So because the disturbance, the net effect is that the disturbance cannot move, what happens is that in this case, or you may interpret it in a certain way. So, if you do not have the velocity of the disturbance, then this reservoir does not understand. This reservoir does not understand that there is a disturbance, and because the reservoir does not understand that there is a disturbance, beyond lowering this pressure below the critical pressure, you will see that the mass flow rate will not increase anymore, because beyond this the disturbance will not be able to reach this reservoir at all. This is a critical condition. Beyond this critical condition, the disturbance will not be able to reach this reservoir. Okay. So, you will find that the velocity of the fluid will, if the velocity of the fluid is greater than c, then if the velocity of the fluid is greater than c, then if you have a positive number plus c, so okay, let us look into it in a different way. Let us say let us just not look into this equation, let us try to understand it more physically. So, when there is a when the fluid is trying to move with a velocity which is greater than c, that means in this direction the fluid is moving say at a velocity 2c, the disturbance at its best is trying to swim against that tide with a velocity of c in the other direction, but because in the forward direction it is already in the velocity 2c, this disturbance against the tide can go only up to c at unit time, but cannot go further. So, the disturbance tries its best with a velocity c relative to the fluid to move here, but the fluid itself is moving so fast that the disturbance against that tide of the movement of the fluid is not able to reach here. That is the physics that I want to convey. So, do not get into the equations, try to understand the physics in a more appropriate way. So, the moral of the outcome of the story is the disturbance does not reach the reservoir. So, if the disturbance does not reach the reservoir beyond this sonic condition, that is for velocity of the fluid greater than the sonic velocity, does not understand that there is a reduction in back pressure. So, even if you reduce the back pressure, the mass flow rate does not increase. So, that means if you want to, not only the mass flow rate does not increase, sometimes it is not the mass flow rate that is your interest always. Mass flow rate for a system mass conservation means mass flow rate for a given pressure will remain the same. What you cannot alter further is basically that through the mass flow rate you could have accelerated the flow, that is what is your objective, that in a high speed application, say aircraft application, had you been able to reduce with a reduction of back pressure. So, this is the direction in which you are having a reduction of back pressure. With a reduction of back pressure, if you could somehow increase the mass flow rate, then you could increase the Mach number in the process, but that you are failing here, you are able to reach only up to Mach number equal to 1. So, that condition is P star. So, what is that m dot maximum? Let us calculate that and we will get something very interesting. So, what is A star here? A star is the area of the exit of the nozzle, because that is where If you are getting a sonic condition, that must be at the minimum area, which is the throat. What is U star? U star is C, right, because Mach number is 1 root over gamma r T star. Rho is, so P by rho is equal to RT. So rho is P by RT. So P star by RT star into A star into root over gamma RT star, right. So this is P star by square root of RT star into A star into square root of gamma, right. Now what is P star? So you have P0 by P, or rather T0 by T. So first let us calculate this. Right, T0 by T was this, right, just check this formula once, 1 plus gamma minus 1 by 2 m square, right. So T0 by T star, what is m star? M star is 1. So gamma plus 1 by 2, and P0 by P is this, okay. So interestingly you can see that this is a function of P0 and T0, because P star is getting a function of P0 and T star is getting a function of T0. So the maximum mass flow rate is dictated in a converging nozzle not by the back pressure but by the stagnation pressure at the reservoir, the stagnation temperature at the reservoir. This is very surprising, because given that this is fixed, the maximum flow rate should be ideally regulated by to what extent you can reduce this back pressure, but it is not. It is eventually related to what is this P0 and T0 that you have at the reservoir, not to what extent you can reduce the back pressure. You may keep on reducing the back pressure, but you will not get any effect at the end. So now we will work out a problem on this converging nozzle and try to understand the phenomenon in a more quantitative way. Air in a large tank at 100 degrees centigrade, 150 kilopascal, exhausts through a converging nozzle that has a throat area of 5 centimeter square. Calculate m dot if Pb is equal to 100 kilopascal, Pb equal to 60 kilopascal and Pb is equal to 30 kilopascal. Okay. So, what we have to do? We have to figure out what is this P star. Is our pressure less than that P star or greater than that P star? If our pressure is less than that P star, then that will not influence the mass flow rate anymore, right. So, what is P star? So, you have a formula for P0 by P star is equal to 1 plus gamma minus or P0 by P is equal to 1 minus gamma minus 1 by 2 m square to the power of gamma by gamma minus 1, right. So, when P equal to P star, m is equal to 1. So, what is that P star? So, if you substitute m is equal to 1, you will get P star because P0 is given. This is P0, this is T0. So, if you calculate it, P0 is 79 kilopascal. You put all the values in this problem. P0 is 79 kilopascal. Sorry, P star is 79 kilopascal. So, when Pb is 100 kilopascal, then m dot is less than m dot max, right, and m dot can be calculated as rho a u. So, when you have Pb is equal to 100 kilopascal, this is greater than P star, which in this case is 79 kilopascal. Now, you have P0 by P, that formula we will use here. So, the question is that at this back pressure, what is the Mach number at the exit of the nozzle, that is what you have to find out. So, we can use this formula straight away. So, this is, if you put the back pressure, then you will get Mach number at the exit. So, this back pressure is 100 kilopascal, P0 is 150 kilopascal. So, from here you will get a value, let me tell from my answer. So, I do not have the exact answer here, but you will get a Mach number. What kind of Mach number it is, greater than 1 or less than 1? This will be less than 1. So, then you have a formula. So, you also need the temperature, because if you know what is the temperature, then you can find out what is the sonic speed, and multiplying that with the Mach number you will get the velocity, and that velocity will give you the mass flow rate. That is the strategy. So, T0 by T is equal to 1 plus gamma minus 1 by 2 m square. So, T0 by Te is equal to this one. So, this value you know from here. So, from here you can get what is Te. Once you know TE, what is m dot rho E A E T E sorry UE. So, this is rho E is P E by R T E into A E into M E square root of gamma R T E. Okay. So, you know everything in this formula. So, you can area M E T E P R for air, all these things you know. So, if you substitute all this, you will get m dot is 0.15 kg per second. For 2 and 3 the answer is the same. Why? Because for both these cases the P is less than P star. So, decreasing the back pressure from 60 to 30 kPa will actually not increase the mass flow rate. So, for the second part, whatever is written here as a theory, this will work. So, you will, so the maximum mass flow rate is this one, P star by square root of R T star into A star into square root of gamma, where P star is a function of P0 and T star is a function of T0. So, if you put P0 T0 here, you will get the maximum flow rate, mass flow rate, which is 0.157 kg per second. So, this numerical problem gives you a physical feel of what maximum can happen in a converging nozzle. You have a back pressure, you reduce the back pressure, there is a critical limit at which you will get the maximum flow rate, where the Mach number at the exit is 1. You cannot accelerate the flow further beyond that in a converging nozzle. But if you want to get a higher level of acceleration, that means you want to accelerate the flow to a higher velocity, then what is required is a converging diverging nozzle. We will discuss the need of the converging diverging nozzle and its design and of design conditions in the next lecture. Thank you very much.